Welcome to Unit 6. This is a unit entitled Systems of Equations. Now what could that possibly mean? What's a system of equations? Well, it turns out a system is just a collection of equations, a bunch of them together. And when we solve a system of equations, we're going to ask the question, what is a solution that will solve all of the equations simultaneously? And the only equations we'll concentrate on are linear equations. And maybe occasionally we'll look at an example of a nonlinear system. But mostly we'll look at linear equations and how to solve a system of them. So that's what we'll be doing coming up. Now, before we talk about solving a system of linear equations, I want to go ahead and talk about systems of linear equations in general. There are a few pieces of terminology we need to get used to, and a few other things that need to be mentioned before we get started into the business of solving them. So, what I'll start out with here on the pad is a motivating example. At least I hope it's motivating. And here's the situation. Imagine that movie tickets sell for $8. And there's a senior discount of $2. Let's let X be the number of tickets that are sold in a given evening, say, at the $8 price. And let's let Y be the number of tickets sold at $6, which is the $8 price minus the senior discount. And suppose overall that 525 tickets were sold, and that overall $3,580 was received. What I want to do is write equations relating X and Y. And I'll solve those at a later time, but right now I just want to write down the equations. So let's go ahead and do that. So the solution to my motivating example is to write out two equations. Well, there were two things that we had in the end. We had a certain amount of money. We had a certain number of tickets that had been sold. So we can really write out two equations. One you might call a revenue equation for the money, and the other one you might just call the numbers equation for the numbers of tickets. So we'll write equations. First of all, I'll write them in English. Total revenue, that's how much money we brought in. Total revenue is equal to, of course, the $8 revenue, the amount of money brought in with the $8 tickets, plus the $6 revenue, the amount of money brought in there. Also, we know that the total number of tickets sold is equal to the $8 sold plus the $6 sold. So as we've done before in word problems, I've written an equation involving the money, an equation involving the numbers. Now let me write out those two equations using the letters that we know from the previous page. Remember, X is the number of tickets sold, and Y is the number of tickets sold. The X at $8, the Y at $6. So in my money equation, I know I ended up with $3,580. And I know that for each ticket of $8 ticket, there were X of those sold, plus the $6 tickets, there were Y of those sold. So there's my total revenue equation. I know for numbers that 525 tickets were sold, and that's simply the sum of the number of tickets X and Y in the two versions. Now this is what's referred to as a system of equations. And please note the notation here that I'm using. This bracket at the end, not at the other end, just at the left end. Okay? Please keep that in mind because we're going to do that throughout this unit. Whenever we solve a system, in order to keep the equations together so that we think about them as a unit, we'll put this bracket here at the left. So this is an example of what one might call a system of two equations in two variables. The two variables being X and Y here. So there's an example of a system of two equations in two variables. Okay, well, now that we've seen this system, what I want to do is define formally what a system of equations is, and then talk about some of the terminology associated with such systems. A system of equations is, well, as I said, it's a collection of two or more equations. That's what I said at the very beginning of this unit. It's just a collection of two or more equations in one or more variables. One or more variables. So you can think of it as a bunch of equations, and that would be fine. Okay? And once again, let me give you yet another example to add to our small collection now. We've got one. Here's a second one. X plus y plus z equals 6. 3x minus 2y plus 4z equals 9. X minus y minus z equals 0. Here's a larger system. Again, I'm using this bracket notation on the left to keep it all together. And you might also notice something else that will be very important as we work through these. Notice these columns here. Notice I put all the x's vertically above one another, all the y's, all the z's, and the constants on the other side of the equal sign. This will be a pattern we're going to adopt later. So you've got the bracket on the left, the equations neatly organized, and this is an example, of course, of 1, 2, 3 equations in 3 unknowns, or 3 variables. And we're going to see more of these. Now, that's what a system of equations looks like, and this is what it's defined to be. What does it mean to solve a system of equations? It means to find a solution, and a solution is also what I said earlier. Let's get that written down. A solution to a system, so solution is what's being defined here. A solution to a system of equations is a set of values, these are real number values for us, for the variables, okay, values for the variables, that, and I like to say it this way, simultaneously make each equation true. Simultaneously make each equation true. Because to solve a system is really, in a sense, harder than solving just a single equation, because you need to satisfy all the equations at the same time. So a solution that works in one equation might not work in another equation. To solve the system, you have to find what solves them all at the same time. And in addition to the solution, a system with one or more solutions, this is kind of the good case, one or more solutions, is called consistent. Okay, that's what's being defined here, consistent. A system with one or more solutions is called consistent. And I guess you can probably guess what I'm going to write now. Otherwise, when it has no solutions, it is called inconsistent. Inconsistent. So, the good case, as I said, is the consistent case, the case where there are some solutions to be found, one or more of them. Inconsistent is when there are no solutions. So, these will be the 2 words that we use as we work throughout. So get used to them, and I'll use them as often as I can so that they'll seem natural. Well, I said we were going to limit ourselves to linear equations, and I need to define what I mean by a linear equation. And you may say, haven't we already done this? Well, we did it really for the case, if you recall, standard form y equals mx plus b. Well, that was one that had 2 variables in it. On occasion, we will have more than 2 variables. So, a linear equation in n variables. Now, this is an unusual concept. We'll need to talk about what this means. A linear equation in n variables, x1, x2, up to xn, has the standard form, a1x1 plus a2x2 plus up to anxn equals b. So the x1 to xn are the variables, and where the coefficients a1, a2 up to an and b are all real numbers, as we've seen. Now let's talk about this, because this is really a different kind of equation than we've seen before. These are n different variables. Now when we do it in practice, as I'll tell you on the next page, we will call them different names. We'll call them xy or xyz, etc. But in general, you could have as many as n of them. And notice that they're all linear, because the power that x1, x2, or xn reach is never greater than 1. It's always equal to 1 here, and all the constants are over gathered on the right. So this is a linear equation in n variables. Now, so you don't worry, we are going to limit ourselves to 2 specific cases. Here, let me write this down. We'll only explore systems. So the only systems we're going to look at, systems of such linear equations. And so we're not going to be looking at systems of nonlinear equations, except in really the mildest form toward the end of this particular unit. We'll look at linear equations mostly, and only the 2 or 3 variable cases. Okay? And we will write more simply ax plus by equals c. So we won't use that subscripted notation and use x1 and x2. We'll use x and y, because that's more familiar to us. Or, in the case of 3, we'll use ax plus by plus cz equals, say, d. Where, as usual, all these coefficients, a, b, c, and d are real numbers. Okay? And please note that this first one is a familiar linear equation that we've seen before. This one can be graphed. It is a 2-variable, therefore 2-dimensional, therefore the plane 2D, this can be graphed in the plane. This is a line. Now it might interest you to know that this is also a line, if you think about it the right way. But we won't be examining any pictures involving this. We'll simply call this a linear equation in 3 variables. And we won't explore the fact that its graph is actually a plane, and that there are some versions that are lines, but we'll talk about that. We won't talk about that in this course. We will graph these, and what we learn about the graphs here, we will apply here. So, speaking of this case that can be graphed, what are the possibilities if you have a system, 2 or 3 variables, and 2 or 3 equations? Well, you're talking about 2 lines or 3 lines. The 2-line case can be graphed. Let me show you what the possibilities are. And I've written this out this way. Graphically, here are the possibilities. If you have 2 lines, which specifically is 2 linear equations in 2 variables, say x and y, these are the only 3 things that can happen. They intersect, they turn out to actually be the same line, or they are parallel lines that don't intersect at all. If they intersect, they have one solution, and they are referred to as independent linear equations, or independent lines. If they are the same, they're called coincident. There's an infinite number of solutions, because everything that satisfies one will satisfy the other one, and lines have infinite number of solutions. So there's an infinite number of solutions, but they are referred to as dependent, because of course they depend on one another. One is a multiple of the other. Together, these that give you one or an infinite number of solutions are called consistent. Now, consistent is the word we'll use most often, and we'll talk about one or many solutions. Finally, there's this parallel case over here. That's when you get no solutions, and these are called inconsistent. So remember, as we're working through these linear equations in 2 variables and we're not drawing pictures, that these are the pictures that happen. and they correspond to 0 solutions for parallel, infinite if they coincide, and 1 if they intersect. For 3 linear equations in 3 variables, we won't draw the same pictures, but it turns out the same 3 possibilities for solutions will hold. And I'll say a word about that later. But let's go ahead now and do an example. Solve graphically. Because we don't have any other ideas about how to solve these at the moment. We will learn methods in the next couple of sections, but right now we'll just solve this in the only way we know. We'll think of these as lines and graph them. So here I've got 2x plus 5 equals 2x plus y equals 5, and minus 4x plus 6y equals 12. Again, I'm using this bracket notation to keep this all together, only on the left. Very good thing to do. Another thing I'm now going to introduce that I recommend you do is you want to label your equations maybe the way I'm doing it, with a 1 and a 2, just to keep in mind which one's which, and then later you can refer to 1 or 2 instead of having to write the equation out. You'll find that this turns out to be handy. So this turns out to be handy. And the bracket here is really necessary for organization purposes. In this solution, all I'm going to do is I'm going to rewrite these in such a way that I can graph them, and then I'm going to graph them. I don't have any other techniques, so that's all I'm going to do. Now, when you move from a system to a modified system, here is the notation I want you to use. Just use an arrow, single arrow like that, and rewrite the system. This time I am solving for y, so you do the solution y equals here, minus 2x plus 5. And in the other one, if you do the work to solve for y here, it's pretty easy. You get 1/6 4x plus 12. Now this is my new 1 and my new 2. Okay. Now I didn't have any technique, so I solved these so that I can now put these in a calculator, or I can graph them based on what I know about lines. And here's what I got. If you do go ahead and graph these, a window that I looked at was -6 to 6 and -2 to 10. And the picture I got was something that looked like this. Here are my axes. There's 1. Here's the other axis. One line looks like this. The other line comes down and looks like this. And there's the intersection point. Which line is which? Well, line 1, which was the y equals minus 2x plus 5 line, is this line. And line 2, which is the y equals 1/6 4x plus 12 line, that one is the other line, which is this one. And the point, what's the point? It is the point that is approximately, to 2 decimals, 1.12, 2.75. And you do this, of course, via trace, etc., or whatever technique you might have on your calculator. So the end result is that I have the solution that x is approximately 1.12 and y is approximately 2.75. And that is the solution, at least approximately, to the original system of 2 equations and 2 unknowns, which turn out to graph and intersect just like that. Now we can't do that, as I said, for the 3 case, but we can note the following fact, which will allow us to deduce the number of solutions nicely. And here's the fact. For a system of 3 linear equations, linear, of course, the only ones we'll look at, in 3 variables. Now these will be 3-space planes or curves, so we won't talk about them in graphical terms. The only possibilities for solutions are, just like in the case of 2 equations and 2 unknowns, 2 linear equations and 2 unknowns, you either get none, you get 1, or you get infinitely many. just as in the two linear equations. Two linear equations in two variables case. Now that is going to make our life much, much easier. In fact, this works for no matter how many equations. If you have n linear equations and n variables, these are the only possibilities for numbers of solutions. So knowing that will make our work a lot easier. All right, when we come back, we'll talk about solving linear systems. We'll actually begin by looking at a particular method, and then after that, we'll talk about a second method. Well, now that we know the words involved with solving systems of linear equations in general, we can now start looking at a technique. And here's the first one we'll look at. Solving a system of 2 or 3 linear equations in 2 or 3 variables. Those will be the only cases we look at. And the first method we'll look at is called substitution. It's not the most useful or most efficient method, but it certainly is the easiest to get across at first. So let's look at it. And in solving a system of linear equations by substitution, we'll look at, as usual, we'll look at the 2 and 3 cases only. Okay? Get my 3 in there. That reads reasonably well. We'll look at the 2 and 3 cases. And the first case we'll look at will be 2 linear equations, just so we're clear on what we're talking about here. 2 linear equations in 2 variables, and the variables we'll use will be x and y. So let me box this in. So this is the segment now we're going to look at, 2 linear equations in 2 variables, x and y. And I'm going to illustrate the method of substitution by example. So my poor little 3 here. And we'll go on and start with our first example. Our first example is this one. And this is the same example we saw before, by the way. And we're now going to solve it a different way. We solved it previously with approximations using graphing. Now we're going to solve by substitution. Solve by substitution. And here's the system, if you remember. It was 2x plus y equals 5, minus 4x plus 6y equals 12. Now we already know the answer from our graphical solution, so it'll be nice to see this confirmed in our substitution solution. Okay, first of all, what I want to do is remind you of notation yet again. Notice I have the bracket on the left but not on the right. That keeps the equations all in one block. Also, I'm going to label them 1 and 2. See, I circled the numbers and labeled them just so I know which equation I want to refer to. It makes my commentary easier to write down. It'll make your commentary easier to write down too. So, in substitution, I will solve for, say, now I say that because you can solve for either variable in either equation. So solve for, say, y in 1, equation 1. Then the technique is to substitute into, that's why it's called substitution, substitute into 2. And here's how it works. I will first of all, I'm going to rewrite this and solve the first one for y. Now that's something we did before, so you know what it is. Y equals minus 2x plus 5. And I'll just rewrite the second equation without making any changes. And now what I want to do is substitute. Because here I have an expression for y, and I will now substitute in for this y here. And then I will have an equation entirely in x that I can solve for x. So that's exactly what I'm going to do here. So I'll take that second equation. This is 2, remember. And this is minus 4x plus 6, and this is where I replace the y, minus 2x plus 5, and then equal 12. And now you see I have an equation in one variable. Minus 4x minus 12x plus 30 equals 12. So that's minus 16x equals minus 18. X is therefore 18 over 16, which is 9/8. So now I have X. Now I had two variables in the system, X and Y, so I need to solve for Y also. And we do what's called back substitution. So back substitute into, say, now the nice thing about substitution is you can pick any equation to substitute into. I can substitute now my X value into any equation along the way. I'm going to substitute back into 1 in the second form that 1 appeared in. Let me bring back the previous page and show you what I mean. Here is the original system of equations up here, and here's what 1 looked like originally. I modified it this way so I could solve for Y. This is the one I'm going to substitute my X back into because it's the easiest one I can see. You always have free choice. You could substitute into any one of these 4. Always choose the easiest one. So substituting back into 1, I get Y equals minus 2 times the X value here, 9/8. That's where this comes into play, plus 5. Well, that's minus 9/4 because the 2 and the 8 give me 4 on the bottom. 20 written in fourths is, 5 written in fourths is 20/4. 20 minus 9 is then 11/4. So now I have Y. And I can pull it all together at the end and say that X is equal to 9/8 and Y is equal to 11/4. And this is an example, if you like, of one of these situations where you have two lines, two linear equations in two variables, and they intersect at one point, and the point I've discovered is that it's the point 9/8, 11/4. So this makes this consistent, because consistent is whenever you have a solution. Inconsistent is when you don't have a solution. And if you take 9/8 and 11/4 and go back and compare with the graphical example we did before, you'll see that these are exactly the correct answers. Okay, that's how substitution works. You substitute and then you back substitute. Let me summarize this. I've written this up to give you the basics for substitution. First thing you want to do is solve for one variable in one equation. It's your choice which variable and your choice which equation. Then you take what you get out of that and substitute the expression into the other equation. Now, or equations, you may have more than one. Now, if some equation has only one variable, solve it for that variable. Otherwise, repeat the process from above until you get an equation that has only one variable. Then once you have that one variable, find the other variable or variables by back substitution, and be sure and check your solution. Now, I didn't check my solution in the last one because we've done the problem already twice. But you want to check your solution in the future. Here's an example. This is a new one. Solve by substitution. And the system is this: 3x minus 2y equals 5, and 5x minus y equals 6. I'll label this equation 1 and this equation 2. And again, notice, just for the record, that I've got my x's vertically aligned, my y's vertically aligned, and my constants vertically aligned. Now, when you start out, it will be very useful to have that. Not so much for substitution, but for the next method, it's crucial. Solution. I always want to tell, and you need to tell yourself and tell your instructor what you're doing when you solve these. It's very important not to just list a bunch of equations. Tell what you're doing, because it'll give you a paper trail, as I've said before, to retrace your work. I'm going to solve for y in 2. That's the second equation this time around. Now, why did I choose 2? Well, it's a little bit easier than 1, and notice that the y doesn't have anything multiplied in front of it. So I figure it'll be easier to solve this for y. But it doesn't make any difference. Mathematically, I could do either one. So if I do that, I repeat the system. There's the arrow saying I'm going from this system to this new system. I'm not doing anything to the first one, so I'm just going to recopy it. The second one now I've solved for y. So y equals 5x minus 6. That one you can do in your head. Then what I'm going to do is, I can even say it this way, I'm going to substitute 2 into 1, because y now is this expression, and I'm going to substitute this value into that y. So if I do that, what I have is 3x minus 2 times 5x minus 6, here's that y being substituted in there, equals 5. And now once again I've reached the stage where I have an equation in one variable, the variable x. So I solve for x, and I get 3x minus 10x, multiplying through, plus 12 equals 5. These add together to give me minus 7x. I move this to that side to get minus 7. X then is equal to 1. So I have the x. I back substitute, because I want to get my other variable too. I back substitute into, say, 2 in its second form, and I'm going to be getting y, and let me bring that back so you can see this. A little easier if you have all of this in front of you at once. Here's my y equals 5x minus 6. I'm using this form instead of the original. That's my choice. And y then is equal to 5 times the x value, which is 1. Here's where the 1 comes in. Minus 6, and so that's minus 1. So pulling this all together, so I have that x is equal to 1 and that y is equal to minus 1. And this is going to be another one of those cases of intersection. The two linear equations in two variables can be thought of as lines, and it is consistent because there is a solution. And in this case, I will leave the check to you. You can try this pair of numbers in the original system and see that it works. Now, before we go on to 3 equations and 3 unknowns, 3 variables, I want you to practice these cases with 2 variables. And we'll come back after you've had a chance to do that. Now with some practice in 2 linear equations and 3 variables, we'll now take that practice and put it into the context of 3 linear equations and 3 variables. Much of this is the same. Organization once again will help. So let's solve by substitution this particular system. X minus y equals 6. 2x minus 3z equals 16. 2y plus z equals 4. And I write the system on the left, the indicator, the brackets, and then 1, 2, 3, I label the equations on the right. Now I hope the very first thing that you noticed is that the variables aren't lined up the way they're supposed to be. See, there's x's and y's mixed up here and y's and z's mixed up here. The first thing I'm going to do, because this is the way these things will turn up in practice, I'm going to organize, say, call it organize vertically. And the reason I'm doing this is because it's a good habit. And like I say, it doesn't matter so very much for substitution, but it matters a great deal for the next technique we'll learn called elimination. But let's try substitution on this. So first I'm going to reorganize it so everything's lined up. So I'll have x minus y, I don't have a z so there'll be a space, equals 6. The next one is 2x minus 3z equals 16. And the third one is 2y plus c equals 4. So there's my system, and now I'll put little arrows here to indicate that I've lined everything up the way it should be. This is equation 1, equation 2, and equation 3. Okay? Now, I want to solve, say, and again I can choose any equation I want. Well, for no good reason, and because it's the first one there, I'll solve, say, number 1 for x. And I will then substitute the result below the first equation, meaning I'll find out a value for x here and then substitute in for x's wherever it occurs below. Now, as you see, it only occurs in the second one. So I'm going to first of all solve for x up there. So this is going to violate my organization. That's okay. As I said, the organization is more important for the next method. So solving for x here, I have x equals 6 plus y. The other two do not change, so I'm simply going to rewrite them. 2x minus 3z is 16, and 2y plus z is equal to 4. You always want to keep everything in place, and remember, these are equations 1, 2, 3 in order. Then I want to take this first one here and substitute. Remember, that's what I do in substitution. I now have an expression here for x, and I will substitute in for this little x in the second equation. Now, the second equation I've labeled 2, so that as I work down my page, I can keep referring to that. In 2, I now do my substitution. 2 times there was an x there, and now replace it with 6 plus y, minus 3z equals 16. Now you see, unlike the equation, the system of equations with 2 equations and two variables, I have still 2 variables floating around. You'll see what I do with this now. Let's simplify this out. This is 12 plus 2y minus 3z equals 16, and then I'll bring the 12 to the other side, and I'll get 2y minus 3z equals 4. Now this is the new revised version of 2. You might call this the new 2. And so now I repeat my whole system to see where I stand. I have here x equals 6 plus y. That was the rewritten x. My new second one here is 2y minus 3z equals 4. That's from here. And the old number 3 is 2y plus z equals 4. So there's my new system, 1, 2, and 3. And I'm not going to try and keep track of when the 1, 2, and 3 get new or old. They're just 1, 2, and 3 at every stage, unless there's an ambiguity I need to fix. So what am I going to do now that I have this system in front of me? Well, I solved for x and gotten rid of all the x's below. I'm going to do the same thing now with y's. So I'm going to solve the second one, say, for y, and then use that y to get rid of the bottom y. So with that in mind, I will then, first of all, in 2, I will solve for y, keeping track of what I'm doing. So my 2 is 2y minus 3z equals 4. So that's 2y is equal to 3z plus 4. And so y is equal to, say, 3 halves z plus 2, because the 2 will divide into the 4. Okay, I have now solved for y, and I want to then substitute into 3. Now 3 was 2 times y plus z equals 4, so I now have a value for y of 3 halves z plus 2 plus z equals 4. Okay? And I multiply that through, I get 3z plus 4 plus z is equal to 4. So I've got 4z equals 0, because if I bring that 4 over, the 4's disappear. And so I end up with z equals 0. And finally, after a little bit of work, I finally have an actual value for one of the variables. Now how do I get the others? I back substitute. I back substitute. And I might even say upwards now. Since I'm starting with z, I'm going to go back up to get first y, then x. Now I'll remind myself that z is equal to 0. And then from equation 2, the last version of 2 or any earlier version, from 2 I've got y is equal to 2 plus 3 halves times z, which is 0. So that becomes 2 for y. And from 1, I can solve for x. X is equal to 6 plus y. So it's now 6 plus 2, which is 8. So putting this all together finally, so we have that x is equal to 8, and y is equal to 2, and z is equal to 0. And these were the only possibilities So this is a case, because we have a solution, we can call it consistent. I won't try and draw the picture because we have 3 variables, and that would be 3 space. So I won't try that, and I'll leave the check to you. So you can confirm that what I've done there is correct. So here's my advice regarding this method and the next. Substitution. Substitution is only sometimes, now let's be clear on this, sometimes useful, and only for easy or fairly easy 2 equations and 2 unknowns, in 2 variables rather, 2 equations in 2 variables, or 3 equations in 3 variables. In general, however, elimination, which is the method that's coming up, elimination is much more efficient. As we'll see. Okay? So we'll finish this segment and come back and do elimination. Okay, we've solved system of linear equations in 2 or 3 variables by a method I've called substitution. I've also said that that is not the most efficient method and not the one you want to use in practice most of the time, except for the easy cases of 2 variables and 2 equations. Generally what you want to use is this method. Solving a system of 2 or 3 linear equations in 2 or 3 variables, the method's called elimination. It is much better organized, it is efficient, and in case you ever start doing these on computers with hundreds of equations and hundreds of variables, that's the method that is implemented there. So this is one we want to learn. So, and I'll even make a mark here that this is preferred. It's a very elegant method, and in fact if you study a course called linear algebra or matrices, you'll learn that there's an application there to this. But we won't talk about matrices in this course. Here's the idea behind elimination, unlike substitution. Now substitution, you recall, we solve for one of the variables somewhere, and we substitute it into the other equations, eventually hoping for an equation where we had a variable equal to a constant, and then we back substitute it. Here's what we're going to do here. We're going to keep replacing, and we'll have to decide how to do that without changing the set of solutions, of course. Keep replacing the equations with equivalent equations. Equivalent but easier equations. And we'll do that by what's called eliminating variables, hence the name, elimination, by eliminating variables as we go until the solution is clear. Okay? And remember what an equivalent equation is. An equation equivalent to a previous equation is one that may look different, but which has the same set of solutions. And that's what we want to be careful when we make our changes to these equations, that we don't alter the solution set. We simply find an equation that's equivalent and hopefully easier. And we'll do that by what's called eliminating variables, and I'll have to show you what I mean by this. Now my advice throughout this is going to be repetitious, stay organized. All of the organization that I use in these problems is recommended for you to think about these problems. Now, the first natural question is, you're telling me that I need to keep replacing the equations with equivalent but easier equations. How do I legitimately replace equations with equivalent ones without changing those solution sets? Well, there'll be a set of rules. 3 rules in all. And let me illustrate them, and then I'll list them all in order. First of all, here's rule 1. Now, rule 1 seems so embarrassingly easy that you don't even think it needs to be stated, but it does, so let me go ahead and mention it. Suppose you have, and I'll do this I'll only illustrate it with the 2 by 2 case, the two linear equations in 2 variable cases. That way I don't have to write so much. a1x plus a2y equals c1. Let's suppose we have this system, and b1x plus b2y equals, say, c2. So there's a system of 2 linear equations in 2 unknowns x and y, 2 variables x and y. Here is what the rule says you are allowed to do, because this will not change the solution set for the system. You are allowed to write the equations in the other order. b1x plus b2y equals c2, a1x plus a2y equals c1. In other words, you can switch these, or if you like, the word interchange. Now that seems, like I said, so embarrassingly simple it's not worth mentioning, but occasionally you're going to want to do that. You're going to want to move the equations up and down to make the picture look better. Okay, so rule 1 was pretty simple. What's rule 2? Well, rule 2 is also simple. Rule 2 goes like this. Suppose you have a system, say a1x plus a2y equals c1, just like I had before, b1x plus b2y equals c2. Okay, so I have a system. This rule says I can multiply either one, but for the sake of this picture, multiply, say, 1, and so this would be the first and that would be the second equation, by some number d that's non-zero. And I will then get a new system where the first one is now d times a1x plus d times a2y equals dc1. And the second one has not changed. Second equation is identically the same. So rule 2 says you can go through your equations and multiply any one of them by a non-zero constant. Sometimes you may want to think of that as dividing out a certain number so that the d times a1 becomes 1, for example, or something else. But multiplying by any non-zero constant is legitimate. And finally, rule 3. Now this is, of the 3, the most complicated, but it's not very complicated. Let's again imagine I start out with a1x plus a2y equals c1, and b1x plus b2y equals c2. Okay, and so these are equations 1 and 2. Now what does rule 3 say? Rule 3 says, there'll be my new system. Rule 3 says replace, say, 2 by 1 plus 2, or 1 minus 2. So I can do that, and so I'm replacing 2. That means 1, the original equation, is not touched. It remains the same, but the second one is now going to be replaced by the sum of the 2, which means, or the difference. So I have a1 plus or minus b1 x plus a2 plus or minus b2 y equals c1 plus or minus c2. So I replace the second equation here by the sum of the 2 equations. Now, why one would do that, you will see later on. It makes things much nicer because you can end up causing variables to disappear. If a1 and b1 are both the same number, then subtracting them will make this 0. And you can also see that I'm replacing the equation and not losing any information. Because you may say, well, 2 seems to be gone now. You have 1 plus 2 here, but where's 2? Well, I could recover 2, couldn't I? By subtracting 1 away from it again, or adding it as the case may be. So the information is not lost, is the point. The information is not lost, but the arrangement now is much better than it was before. So you have these 3 rules. One rule says you can switch equations. Another one says you can multiply any equation by a non-zero constant. And the third one says you can take and add or subtract the equations in any way you like and replace other equations with those sums or differences. So let me bring my list here of what I just said. Rules for creating equivalent equations. Those are equations that have the same solution set as the original equations. You may, 1, interchange or switch any 2 equations. You may multiply each side of an equation by a non-zero constant. And the third and most useful one, the one we use most often, replace any equation by the sum or difference of that equation and any other equation in the system. And no information will be lost by that process. And of course you combine all of these. So you may replace an equation not by the sum and difference of two, but by the sum of one and 6 times the other one, for example, using the multiplication and the replacement together. So all of these rules get used together. And I will again start with the case of two linear equations in two variables where everything is much simpler. And the two variables will be x and y again. And then later we'll apply it to the case of three linear equations in three variables. All right, here's my example. I want to solve by elimination now, not by substitution. So solve by elimination. And this is the movie problem we saw earlier. The movie problem, where we sold movie tickets. And if you remember what the system was there, it was 8x plus 6y equals 3580, and then x plus y equals 525. And you can recall where these come from. This was the money or revenue equation. That was the amount of money we got at the end, $3,580, and this was the number of tickets. There were 525 tickets sold. Now, none of that matters to us right now as we try and solve this system. Please notice that I've got my x's lined up, my y's lined up, so my x's are lined up vertically, my y's are lined up vertically, and my constants are also lined up vertically on the other side of the equal sign. This is the method where it is crucial that you keep that organization. That's what I mean by staying organized. Okay, in the solution, first of all, you have to choose a variable to eliminate. And I still haven't explained elimination, but I am just about to get to it. You need to choose a variable to eliminate. Usually people choose x, and then they go to y, and then z, and all the other ones in that order. But it really makes no difference. But for example, in this one, choose a variable to eliminate. Just to be different, let's say y. And we'll eliminate it from equation 2. So again, this is equation 1 and equation 2. It's good to number them. All right. So in order to do that, that's my goal. See, this is my overall strategy. The first thing I'm going to do toward that end is I'm going to first multiply equation 2 by minus 6. Now please note that I'm telling you what I'm doing, and I'm using representations for the equations to make my life easier here. And now I'm going to multiply that second equation by minus 6. That will not change the first equation. So rewriting what I've got now, I have 8x plus 6y equals 3580. That's the first equation unchanged. The second one multiplied by 6 is now minus 6x minus 6y equals minus 3150 if you multiply that 6 by the 525. This is now my 1 and my 2 equations. Now, you should see why I did this now. This is why I did this. I'm trying to eliminate y, right? I now have plus 6y and minus 6y. The natural next thing to do is to use that rule 3 we talked about. And rule 3 says, in this case, replace 2, the second equation, by 1 plus 2. Now, sometimes you want to take this calculation for the 1 plus 2 off to the side before you come back to the system. Now, in this one, it's so easy, I can just add the 2 right there and keep track what I'm doing. Now, remember, I am not changing 1, so it's still 8x plus 6y equals 3580. 1 is not changed. However, the second one is going to be replaced by the sum. So let's do the sum. And what do I have? I get 2x plus, this part is 0 by design, 6y and minus 6y add to 0, equals, and then I want to add these two. So 3580 minus 3150 is 430. And now you see the advantage. The second equation has no y value. I have eliminated y, and that's exactly what I was trying to do. Now, this last one can be immediately simplified. Simplify, say, as x equals the half of that, 215, and I have x. Now, how do I get y? Well, I get y in the same way that I've gotten y in the substitution case. That doesn't change. Back substitute. Back substitute into, say, 2. Original 2 to get y. It doesn't matter which one you use, that's just the one I picked. And if I do that, the original 2 is, if you recall, what it was x plus y equals 525. That was the original. And I chose that because everything's simple there. Now I know what x is. I now have 215 plus y equals 525. So y then is equal to 310. And so we are done. We have, to put it together, x equals 215. These were the $8 tickets, if you remember the original problem. And y now is 310, and these were the $6 tickets. And this is another one of those cases, two equations with two variables that is a cross like that. So it's the intersection case, and so this is consistent. And I will leave the check to you. You can go ahead and try these numbers to see if they actually work. But now we solved that original equation we started with a long time ago with the movie tickets. Let me apply this elimination another time so you can begin to see how this works. Solve by elimination. And then you'll have a chance to try one on your own coming up. Solve by elimination. 2x plus y equals 5. 4x plus 2y equals 8. So this would be equation 1 and this would be equation 2. Okay, solution. Well, I'm going to do the same thing I've done before. Let's eliminate. I just pick a variable. Let's eliminate, say, this time x, and we'll eliminate it from the second one. Usually you try and leave your first equation alone and eliminate from the second one. Now, you're not always lucky enough for that to work out that way. But then again, you do have the rule that says you can switch the order of the equations, so you can make it work out that way. Okay, in order to do that, what I'm going to do is I'm going to multiply 1 by minus 2. Now, why am I doing that? Because if I multiply 1 by minus 2, I'll have a minus 4x. Then later, when I add it to 4x, I'll get 0. And that's what I'm headed toward. So my system now becomes minus 4x minus 2y equals minus 10. Remember, I multiplied 1 by minus 2. That's what happens to these three. The bottom does not change, so it's 4x plus 2y equals 8. And that's equation 2, just reminding myself. Now I'll do what I set out to do earlier. I remember I'm trying to eliminate the x's here. I'm going to replace 2 by 1 plus 2. Okay, so let me do that. I will now have a new system, and 1, the original equation, is not changing, so it's still minus 4x minus 2y equals minus 10. And now let me bring back what I had a moment ago so you'll see what I'm about to do. There's the system, the last system I had, and I want to replace 2 by the sum of them. So I'm going to add vertically here and replace the second equation by what I get. Now minus 4x and 4x will give me nothing. You may also have noticed that minus 2y and 2y will give me nothing. So I end up with 0 on this side of the equation. On the other side, minus 10 and 8 give me minus 2. Well, you know, that's a problem, because that is a contradiction. Now, what happened here? I didn't make a mistake. There's no error here. What has happened is that I ended up with a contradiction. Remember, this is an equivalent system of equations. Equivalent to what? To the original system. Which means if this system of equations contains a contradiction, the original one does also. Contradiction means something that can't happen, meaning there can be no solutions. So, the conclusion? No solutions. Now, since these were two equations that were lines, we're talking about parallel lines. Okay? There are no solutions here. This is what's called an inconsistent system of equations. And that will happen, and the way you'll usually see the problem is right here. You will come up with an equation that is a contradiction. And if you see that, you know immediately that you have no solutions. Okay. Let us try another one. I want to show you all the different kinds of things that can happen here. Solve by elimination. Here's another one. Here's the system 2x plus y equals 4 and minus 6x minus 3y equals minus 12. Equation 1, equation 2. Okay, everything's lined up neatly. Solution, let me just proceed forward in the way that I have been. Let us choose to eliminate, say, I always put say in there because it could be either variable. Let's say x from 2, as we did before. And my goal is that, so my first tactic is to multiply 1 by minus 3. So I get a new system. I have minus 6x minus 3y equals, actually, let's see, I should have multiplied just by plus 3. How about that? That'll make that easier. That'll make that 6x plus 3y equals 12. And then the second equation has not been touched, so it's minus 6x minus 3y equals minus 12. Then I will replace, just continuing onward here, I'll replace 2 by 1 plus 2. And I can slip that in right here because you see what's going to happen. The first one, 6x plus 3y equals 12, is not changed. I'm replacing 2 after all. And if I replace 2 by 1 plus 2, what happens? I get 0, I get 0 here, and I get 0 here. So I have 0 equals 0. Now, there's nothing wrong with that. That's correct. So what does one conclude from this situation? Due to that, we see that this is a case of, this is consistent, and there's an infinite number of solutions because they're both the same equation. Okay, what you have is a situation in which you have the same equation written twice. Although you think you've got two equations, you really only have one. And so the solutions are all the solutions to this equation, which is a single line, and all of its solutions, there's an infinite number of them, are solutions to this so-called system. So although this is not really a system, it wasn't discovered to not be a system until we've done a little extra work. Okay, now that's all how to do elimination on two linear equations in two variables. You should practice this now before we attack the 3 case, which will be coming up soon. Now we'll look at the case of 3 linear equations in 3 variables, and we'll try elimination on this case. Now this is where elimination becomes more and more obviously the best or most efficient technique. Example, solve by elimination. Okay, solve by elimination. And here's my system. X plus y minus z equals minus 1. 4x minus 3y plus 2z equals 16. 2x minus 2y minus 3z equals 5. So I have equations 1, 2, and 3. 3 equations in 3 variables, and note that everything is neatly organized. My x's are lined up, my y's, my z's, and my constants. Okay, solution. Well, here is the usual plan. Let me just, since we haven't done one of these with 3, so here's the usual plan that you want to use in attacking these sorts of problems. Usual plan. First try and eliminate x from 2 and 3. Then, continuing on downward, y from 3. So, the last equation then involves only z. The last equation involves only z. And once it involves only z, you can solve for z and back substitute. Okay? So we can then say then back substitute. Now, what is the form that we're sort of heading toward? Notice that if I eliminate, let me box in what we're going to try and eliminate. We're going to try and eliminate the x's down here, and then later the y's down here. And you see what we're left with is this kind of triangular form here on the left, where we have 3 things here, 2, and then 1. So we're coming down like this, and let me go ahead and draw you a picture. The form that we're trying to get to is something that looks like this. It's a triangle here on the left, and then you've got your constants here on the right. So this is kind of the form we're looking for, where everything here is gone. It's all zeros. Now, that is a particularly nice form because down here at the point, you have z equals a constant, and then back substituting, this is back substituting, is going back upwards. So you create this triangular form and then you go back upwards. So that's kind of the strategy you want to try and follow. And remember, you can always get it to work out this way because you can rearrange the original equations in whatever order you like. Okay, in this particular problem, first I want to eliminate x from 2. Okay, so I'm going to replace 2 by minus 4 times 1 plus 2. Okay, and let me bring back the original system because I know it's hard to remember from page to page here. Here is the original system. What I'm going to do is I'm going to multiply 1 here by minus 4. Then later on, and then I will replace this line by the sum of these two, because that will then be minus 4x. Adding to 4x will be 0, and so I will have eliminated this in my next step. So that's what I've said here in my first stage. Replace 2 by minus 4, 1, plus 2. Now this is something you want to calculate off to the side somewhere. Don't try to do it within the system. So for example, what I'm going to do here is say the following. What is that minus 4 times 1 plus 2? That is minus 4 times 1. I go back and I look and I rewrite minus 4x minus 4y plus 4z equals 4, multiplying through from the previous page. And then that, what is 2? 2 is 4x minus 3y plus 2z equals 16. And then I want to add these two, right? Now the first thing by design will be 0. So this part here is by design, okay, by design of the method. So I'll get nothing there. Here I'll get minus 7y. Here I'll get plus 6z. And what I get over here, of course, is 4 plus 16 is 20. So what is this now? This, if you like, is the new 2. I've replaced the old 2 by this expression, and this is the new 2. I want to keep track of that because I want to do the 3 also, and then I'll put it all together in a new system. Also, eliminate x from 3. Okay? And the way to do that is to replace 3 by what? by minus 2 times 1 plus 3. Okay, this expression here, which I will have to calculate out, minus 2 times 1 plus 3 is, but let me show you again why that's what I want to do. Minus 2 times 1 plus 3, come back to the original. If I multiply the first by minus 2, that'll give me minus 2x. If I then add it to 2x, I'll get 0. And that's equation 3. So I'm multiplying this by minus 2 and adding here to get 0. Okay? So that's the technique I want to use. So multiplying the first one by minus 2, I get minus 2x minus 2y plus 2z equals 2. Then the second equation is 2x minus 2y minus 3z equals 5. And then I want to add these two equations. Again, this happens to be 0 by design. That was the idea. Here I get minus 4y. Here I get minus c, and 2 and 5 add to 7. So this equation here, you might call it your new 3. Okay, I have a new 2 now and a new 3. And please remember, let me bring back the original one more time. Throughout all of this, I used 1 to modify the others, but 1 is still 1. It hasn't changed. So when I write down my new system, it is still going to be the same. But I will have a new 2 and a new 3. Okay, so we have, at this point, sort of summarize, we have the first equation, x plus y minus c equals minus 1. That's 1 untouched from the beginning. Then I have the new 2, which is minus 7y plus 6c equals 20. And the new 3, which is minus 4y minus c equals 7. So this is now 1, 2, and 3. I'm just going to start labeling them that from there and forget about where they came from. Now I have this new system, and I want to do the same process, except now I'm going to try to eliminate this y, because I'm trying to build this triangular form. So I want to eliminate y from the third equation, equation 3. Now, what you can do, if you think about this, what do I want to do? I want to somehow multiply 2 by something to get rid of the minus 4. Well, I would have to multiply minus 7y by what? 4 over 7, or minus 4 over 7, to get this in the form of 4y, which would add to minus 4y to be 0. Well, I'd rather not deal with fractions if I can help it. So, now there's nothing wrong with fractions, and you can work the problem that way. But if you see this beforehand, you might say the following. To avoid fractions, first, multiply. You want to try to find something that will make both of these multiply each other out. Subtract each other out eventually. So for multiply, say, 2 by minus 4 and 3 by 7. Now if you do that, this is system up here. I'm going to multiply the second one by minus 4, this equation by minus 4, and this one by 7. If you'll allow me to do that here on the next page, I will have the original 1 untouched again. Let me rewrite it. Equals minus 1 there. And I'm multiplying the second one by minus 4. That will make this 28y minus 24z equals a minus 80. And the bottom one I'm multiplying by 7, so I'll have minus 28y minus 7z equals 49. So here's my new 1, 2, and 3. And you can see why I did it, because in the next stage those are going to add to 0. And I will be nearly done. So I want to write it out first. Replace 3 by 2 plus 3. And I can do this in my head. I don't need scratch work for this. X plus y minus z equals minus 1. So let me draw a line here so you can follow this. That first equation does not change. The second equation also does not change. 28y minus 24z equals minus 80. But now I'm adding these two and using that to replace 3. 28 minus 28 give me 0 here. That's by design. Minus 24 and minus 7, when they add, when you add these two, you're going to get minus 31z equals, and minus 80 and 49 come to be minus 31. So I can see immediately from this last one, if I do a quick simplification, that z must be equal to 1. And you can see that this triangular form here has appeared, the one I said I was trying to get to. And I've done an extra simplification here to get z equals 1. And now what do I want to do? I want to go back up with back substitution. So, doing that to finally finish this off, so with z equal 1, just to get it on this page, back substitute to get x and y, and here's what will happen. In 2, I've got the expression, this is the original 2, I might add, and actually this is, well, one stage, 2. This is one of the many 2's we had. I took the easiest one I found, 7y minus 6 times z, and that's 1, that's where the z comes in, equals minus 20. We had several 2's along the way and several 3's. Remember, you can substitute into any one of them you like. So I picked the one that was simplest. So I get 7y here, because I'm bringing this over to that side, equals minus 14. And so y then is minus 2. So I have z and y. I go back to 1, and that is the original 1. X plus y, which is minus 2, that comes in here, minus z, and that's where the z comes in, equals a minus 1. So I have here x minus 3 equals minus 1, so x is equal to 2. Finally, I have all of them, so I can write them down in one place. X equals 2, and y equals minus 2, and z equals 1. So this is a case where it is consistent because there is a solution. There is only one solution, and since it is 3 variables, I'm not going to attempt any kind of graphing here. I'm simply going to note that it's consistent and that I've found a solution. So this is an example of how to do elimination with 3 variables and 3 unknowns. Here was the original, remember, the original that we tried to solve by elimination. The goal was to try and get rid of these x's and then this y. So we got that nice triangular form with a z value. We found out z was equal to 1. And then we back substituted up this way, which is how we ended up getting x equal 2, y equal minus 2, and z equal 1. Takes a bit of work, but if you're organized, this is not so bad. It's time for you to try some of these problems.